Welcome to Math with Mrs. Bibb. Today we will be learning about polynomial functions. Graphs of polynomial functions, sometimes called power functions, f of x equals a times x to the n power, have common characteristics based on a, that's called the leading coefficient, and n, that's called your degree. Our leading coefficient will tell us if the graph points up or down. It will tell us if the right side points up or the right side is down. Basically, all of this I could have said in much simpler terms, and that is end behavior. And remember, you should be writing down what I write down. So when I check these notes, I should see all those words written down. And then your degree will tell you whether both ends point up or down, or if the ends point in opposite directions. Example 1. Using f of x equals negative 2x cubed and using the leading coefficient degree and state the domain and range. That is not worded very well. I think this should say find. Find the leading coefficient degree and state the domain and range. Okay, so the leading coefficient is negative 2. The degree is 3, which is an odd degree. Odd degree functions, if you'll write this on the side somewhere, odd degree functions, their ends point in opposite directions. And if your leading coefficient is positive, then the ends will look like this. I'm going to draw the coordinate plane in a different color. So there's my coordinate plane. Make sure you draw that. And the ends point in opposite directions with the right side pointing up and the left side pointing down. Right side pointing up, left side pointing down. If your leading coefficient is negative and you have an odd degree, it will be the opposite. Your left side will point up and your right side will point down, which will help us with our domain and range. And let me do even degree. I know this one is odd, but let me write out even degree for us. So for our even degree function, maybe I can do that here. I hope I can squeeze it. Hopefully you left space too to squeeze it in there. So if it's an even degree function, the ends point the same direction. Hope this works out. Okay, and If our a value is positive, I think you can zoom in if you need to, then both of our ends will point up. That means it's not a reflection across the x-axis. If our a value is negative, then the ends point, both ends point down for an even degree function. Okay, so for the next one, state the domain and the range. So the domain, let's talk about what that will look like. My leading coefficient is negative. Leading coefficient negative, odd degree. Leading coefficient negative, odd degree. So how far left or right would this graph open? Well, hopefully you can tell that it's going to open forever to the left and forever to the right. So that would be negative infinity to positive infinity. And then for our range, how far up and down does this graph go? It goes forever up and forever down. So that one is also negative infinity to positive infinity for the domain and the range. Okay, moving on to the next one. A polynomial in one variable is always written in, I believe the textbook said standard form. Which means your exponents go in descending order, largest to smallest. Exponents are positive integers, which means you cannot have a variable in the denominator. That would mean you'd have a negative exponent, like this. X to the negative 1 is when you have a variable in the denominator. You cannot have a fraction exponent, like this. That means you have the square root of x. You'll often hear that said as you can't have a variable under a radical to be a polynomial in one variable. I think that's all the stipulations. If we have more, we'll add more later on, but that's all for now. And then the degree of a function actually tells you what the end behavior looks like. You would need the leading coefficient to exactly name that end behavior. And then there are some polynomials that you need to know. That would be a constant function. That means that you have no x. For example, y equals 3. That's a constant function. A linear function means you have a degree of 1. So y equals x, that is a linear function. A quadratic function means you have a degree of 2. Y equals x squared. A quartic function means you have a degree of 4. Y equals x to the 4th. And a quintic function means you have a degree of 5. And y equals x to the 5th is an example. You cannot have two variables multiplied. That's not a polynomial in one variable. And that, for example, means x times y. You cannot have x times y. So for these problems, we're going to state the degree, leading coefficient, of each polynomial in one variable. Okay, let's do that. If it is, because there may be some that's not a polynomial in one variable. And I just thought of something we need to add to that list over there. Now back to these polynomials, hopefully in one variable. We're going to check to see first, before we do what it asks, if these are polynomials in one variable. So let's check that. Letter A, is there one variable there? Yes. X is my variable, and it has all positive exponents, so that is a polynomial in one variable. Letter B, is that a polynomial in one variable? X is my only variable. You could also have Y, but we're focusing on X. X is my variable, and the only degree there I have is positive. For letter C, this one is not a polynomial in one variable, and that is because X and Y are being multiplied. So please write that down. You have enough space there to write that. So I don't have to name the degree and the leading coefficient because it's not a polynomial in one variable. Then for letter D, is that a polynomial in one variable? Yes, it is. So I will name the degree and the leading coefficient of that. And then for letter E, is that a polynomial in one variable? So looking at it, I can see that this makes it not a polynomial in one variable. So not a polynomial in one variable because X is in the denominator. Which means with X in the denominator, that means you have a negative exponent. And that makes it not a polynomial in one variable. So this one, we do not have to name the degree and the leading coefficient. So I'm going to put degree and leading coefficient. I'll do that on all of these. We have to do that for A, B, and D. Remember, your degree is the largest exponent, and your leading coefficient is the coefficient that's in the front. Okay, for letter A, the degree is 4. That's the largest exponent. And the leading coefficient is the coefficient that is with the variable with the degree. So 2 is my leading coefficient. And then for the second one, letter B, the largest exponent is 3, so my degree is 3, and the leading coefficient is 7 because that's the coefficient that's with the variable with the largest exponent, or with the degree. So 3 was the degree, and 7 is my leading coefficient. And then for letter D, my largest exponent is 5. And then the coefficient that's with that term that has a degree of 5 is 1. So my degree is 5, and my leading coefficient is 1. Hopefully I've left enough room on your paper that you'll be able to do this next thing for me. I never thought about it when I was typing your notes. I want to name the end behavior for all of those that were a polynomial in one variable. I know we've discussed end behavior before, but I just want to go over that to let you see how the larger degrees affects the end behavior. I am going to draw a graph, sort of a graph, for the ones that I'm going to do. And the first one I'm going to do is letter A. And as I look at letter A, the degree is 4, which tells me the ends point in the same direction. So they're either both pointing up or both pointing down. The leading coefficient of positive 2 then tells me that my ends point up. So whatever the middle would look like between those two arrows, it doesn't matter. It doesn't affect my end behavior. But both ends will point up. So my end behavior is, as x approaches infinity, y will also approach infinity, and I'll put f of x there. As x approaches negative infinity, y will also approach positive infinity. So let's go write that. So my end behavior, as x approaches positive infinity, y approaches positive infinity. This means the end's going up. As x approaches negative infinity, y approaches positive infinity. So again, to reiterate, this tells me both my ends are pointing up. Now let's look at the second one. Well, I want to do B and D. That's what I should have said. I want to do B and D. You'll see the reason why I can do B and D at the same time. If you look at the degree of both B and D, those are odd degree polynomials, which means that their ends behave in the same way despite any numbers that are there. The ends of the graph will behave the same way. Odd degree functions, the ends point in opposite directions. And the leading coefficient then tells me what happens with those ends. Since my leading coefficients are both positive, then I know that the right end points up and the left end points down. No matter what's in between these two ends, the right end will point up and the left end will point down based solely on the degree and the leading coefficient. So let's name that end behavior. As x approaches positive infinity, that y end is going up, so it's also approaching positive infinity. And then as x approaches negative infinity, y for this one is approaching negative infinity because that end is going down. Hopefully you can see this end points up, this end points down. So we are going to look at example 4. We're going to use the graphs to state the number of real zeros. We're going to identify the leading coefficient as positive or negative and the degree as even or odd. So let's do some writing. We'll put the zeros, we'll put a Z, we'll put LC for leading coefficient, and then we'll put lowercase d for degree. I think we did capital D for domain. And we'll put that underneath each of these zeros. Make sure you know that that's what we're putting them there for. Zeros, leading coefficient, and the degree. We'll do that for each of these. Zeros, leading coefficient, and degree. Zeros, leading coefficient, degree. Okay, I'm almost there. Okay. The zeros. For this one, for the first one, it crosses, remember the zeros, let's write that out. The zeros are the solutions, the roots, please make sure you write that down, roots, x-intercepts, those all are the same thing. So we're looking at the x-intercepts. Here's x-intercept, x-intercept, x-intercept. So I definitely can tell 4 is an x-intercept. I'm going to estimate positive 1, and this line right here is just, this line here is, I don't know what that is, but I believe that's negative 2. So negative 2, 1, and 4 are the zeros. The leading coefficient, because the right end points up, then I know the leading coefficient is positive. And since both ends point in opposite directions, then I know the degree is odd. So you may want to write how we knew the degree was odd, opposite directions for the ends. Okay, so for the next one, I'm going to kind of hop around. The degree is even because the ends point in the same direction. Our leading coefficient is positive because the ends point up. The zeros appear to be negative 5, negative 3, 3, and 5. Negative 5, negative 3, 3, and 5. For the next one, I just found that graph somewhere, so I'm going to say C circled, or C circles. Hold on. C circles, because we don't have any way to measure or see exactly where it crosses. So it crosses there, and I believe it only crosses here. I don't think it crosses, let me trace that. I don't think it crosses here or here. So I think it just crosses there at 0, 0, and then here. So there are 3 solutions. The leading coefficient is negative, and that's because of this end. That's what makes it negative. And then the degree is odd because the ends are pointing in opposite directions. For the next one, the zeros appear to be negative 1, negative 1/2, 1 and 2. Negative 1, negative 1/2, 1 and 2. The leading coefficient is positive because both ends point up. And the degree is even because both ends are pointing up. They're pointing in the same direction. For the next one, the zeros are, looks like we're going by 2s. So negative 2 and negative 6. I can tell that the leading coefficient is negative because both ends point down. And the the degree is even because the ends point in the same direction. And the last one, my zeros are negative 1 and 2. And the leading coefficient is positive because the right side points up, and the degree is odd because the ends point in opposite directions. Now, one more thing I want to point out, and then we'll be done with this set of notes. I want to point out when you have what is called a double root. A double root is when the graph touches the x-axis and doesn't intersect it. It just touches it and then it turns and goes down. So a double root is where the x-intercept touches. Can you tell by looking at all 6 of those graphs which one or ones has a double root? And I'm going to circle it in blue, or green. I'll circle it in green. This one here is a double root. And I'm going to draw an arrow there because it touches at negative 1 instead of crosses. So a double root is where the graph just touches and does not fully intersect the x-axis. Okay, I hope you have a wonderful day.